Thus far, we've been talking about rigid transformations. Remind me, what are rigid transformations? Good. Transformations that don't change the actual figure. I like that word. They don't change the original image to do anything other than move. We reflect it, we rotate it, or we translate it, or we do a combination of those things. But it does not change the overall size and shape. You get the same thing back. What's another word for congruent? The same. Okay, so we get things that are congruent when we make rigid transformations. Dilations are different. So before this, you didn't have anything else to compare it to. Dilations are slightly different. So when you go to your eye doctor and they dilate your eyes, nobody likes it, right? They may not have had it done. You may have the eye doctors with the fancy machines that don't require dilation. But what does it do to your pupil of your eye? Makes it bigger so that they can see inside the cornea of your eye. Dilation, in this case, does the same thing, or it may contract it and make it smaller. As far as geometry is concerned, a dilation is a transformation in which the figure is enlarged or reduced with respect to a center C and a scale factor K. Put this in your own words. You don't have to copy these verbatim just because they're up here. Dilations make things bigger or smaller based on a scale factor. So here's an example. I have a little triangle down here at the bottom. And I have a point C about which I'm going to dilate it. Okay? You've all done perspective drawing sometime in art class, right? With a vanishing point to make things look 3D. Okay? Same idea here. We're taking a set of lines that are coming out from C, and we're making the figure bigger or smaller based on those lines. Okay? If I go outside here, it's going to be bigger. If I stay within here, I can make it smaller. Okay? So if I make something that is parallel to PR and something that's parallel to RQ and something that's parallel to PQ, I get a new figure. Okay? That's larger than the original. So it is not a rigid transformation. This is a dilation. Okay? So here's how it looks when we animate. Okay? The key thing to be aware of is that the distance from the point that we're dilating from to the new point is going to be equal to some scale factor times the original distance from C to R. Okay? All right, that's the formal definition of it. Let's see it in how it works. But one thing to remember is that K will always be either the distance between the original C and the new point divided by C to the original point, or the image length versus the pre-image length, depending on how they give it to you. So you always want to write the new divided by the old. Pre-image over image means take your new length divided by your old length. Okay? Everybody good? Very good. Now, one thing to be aware of is that a dilation is similar to the pre-image. Your image is similar to the pre-image, not congruent, similar. meaning that the angle measures remain the same, but the links themselves are much larger or smaller. The side links change. Okay? No, one back, sorry. So we'll be talking about similar figures this time, not congruent figures. Okay, everybody ready? So if your scale factor, if k is bigger than 1, it's an enlargement. It gets bigger. Okay? If your scale factor is between 0 and 1, it's a reduction. It gets smaller. What's the number between 0 and 1? 0.5, 1/2, right? 1/4, 3/4. Okay? 0.75, 0.6. All of those will make a reduction. It's making it smaller. Just like the blueprints of your house. Thank goodness they're not the full size of your house, right? You need a crane and a forklift to roll those blueprints up and put them someplace. They're a reduction because their scale factor is smaller than 1. Okay? So here's an original image, pre-image. And now we have performed a dilation on it. So here's our final image. What is K here? Greater than 1 because it's enlarged, right? So my original side CD was 2. My new side CD is 4. So what's my scale factor here? 2. Okay. Here's a new figure, trapezoid. GH has a length of 12. That's the pre-image. G prime H prime has a length of 3. Old divided by new. Sorry, new divided by old is always what you're looking for here. Because was this a shrink or a stretch? Yep, it's a reduction, right? Okay, so we reduced it by how much? 1/4. 3/12 reduces to 1/4. So its scale factor, its K, is 1/4. Okay? So trapezoid J prime, K prime, L prime, M prime is a dilation of image JKLM. The center of the dilation is the origin, 0, 0. Is the dilation a reduction or an enlargement? Reduction. My original was the blue. My image is the orange, and it's definitely a reduction. What's the scale factor of the dilation? Good. How did you get 1/2? So you found a convenient pair of points. The origin to J prime was a distance or a length of 1. Okay. The origin to J was a length or distance of 2. And we said it's a reduction. So we take the new divided by the old. And get 1/2. So find a convenient pair of points. Okay, we could have done the same thing with K. Origin to K was 4. Origin to my new K, K prime, was 2. So new divided by old, 2 divided by 4, 1/2. Okay. Calculating dilation points. You can find the dilation image of any point P with xy coordinates by multiplying the coordinates of P by the scale factor K to get your new P prime. So we want to graph triangle PQR with vertices P at 0, 2, Q at 1, 0, and R at 2, 2, and then find its image after we have a dilation with a scale factor of 3. So we'll start by plotting our points. P was 0 over 2 up. Q was 1 over 0 up. And R is 2, 2. Ballerina point. We'll draw our triangle. Okay. And now we want to find the dilation of it. Michael, what's the scale factor on this dilation? Scale factor of 3. So what are we going to do to find our new points? If P is 0, 2, our P prime will be what? It says to take 3 times the x and 3 times the y. So 0, 6 will be our new P prime. Okay. So plot P prime, 0 over 6 up. Q, 1 over 0 up. What's it going to be with a scale factor of 3? 3, 0. 3 over 0 up. R is the point 2, 2. 6, 6. Draw your triangle. I'm not doing a good job of drawing a straight line. Are they congruent? No, congruent means equal lengths, right? They're not congruent. What are they? Dilations. What's another word for it? Similar. They're an enlargement. So these are similar triangles. Okay. So they can ask us to go one way. They can ask us to come back. They can give us the points and now say, let's use a scale factor of 1/2. So my original P was 4 over 2 up. If my original P was 4 over 2 up, what's P prime going to be? 2 over 1 up. Take half of each coordinate. So 2 over 1 up. Okay. Next one. What's the coordinate of Z, Alex? Very good. So Z was -4, 5. So what happens when we apply a half scale factor to it? What will we get, T? When we take half of -4, we'll get -2. Half of 5, 2.5. So we'll be 2 back, 2.5 up. Label it Z prime. Ian, what's my point G? 1, -3. So if G was 1, -3, Brandon, what's G prime going to be? .5, -1.5. Good. So we're a half of the way to the right, 1.5 down, be in the middle of that box, and we're going to label that G prime. Similar. Reduction, dilation. One more thing they can ask us to do. You can throw a negative into it. So when we throw a negative into it, Peyton, what's my point P's values here? Or what's my coordinate for P's? P. 4, 2. So what's my new P going to be? So if we take a scale factor of -1/4 times it, what are we going to get? -1. And what's 2 times 1/4? Or 2 times -1/4? -2/4, which is -1/2. Okay. When we do reductions, a lot of times they are. Okay. But these are easier fractions. They're not ridiculously hard. We're not talking about fifths and things like that, because they would be hard to graph. So 1 back, 1 down, 1/2 down. There's our new P. Okay. Braxton, what was our original point Z? -4, 5. So what will our new Z be? Jake. I take -4 times -1/4. +1, good. And if we take 5 times -1/4, what will we get, Laura? -1.5, good. Okay. Actually, -1.25. 5 divided by 4 is 1.25. It's not easy, is it? So we're going to go 1 over and then half of a half. So 1 down and half of a half, a fourth, will be down here. And that's our Z prime. As long as you're close, you bet. Okay? The thickness of your pencil can throw things off. Okay? Then the last one. What's our last point? G. So, Maddie, what's G's coordinate, or what are G's coordinates? 1, -3. So, who wants to tackle that one? What will G prime's coordinates be? Maddie, want to tackle that one? William does. -1/4. You could call it 0.25, and then positive 0.75. So 1/4 back and 3/4 up. And there is our G prime. It does not look the same at all. They're still similar, but because of that negative, it's changed things. It's like a 180-degree rotation because it negated them both. Okay. A rotation along with a dilation. All right, last example. Yes, this looks even worse on the screen, doesn't it? You see this all the time in your science books, don't you? Cells being enlarged under a microscope. So if we're asking you about a magnified spider, and when we've magnified it, it's 1.5 centimeters on your paper, and it's 6 times the original size, how would we figure out how big it actually is in real life? 1.5. What are we going to do to the 1.5? Times it by 6. Will that make it larger or smaller? Larger. So we want to know how much it is in original size. We're dividing by 6. Okay? So when we divide by 6, we get 0.25. And 0.25 centimeters, how much is that in millimeters? 2.5, 2.5 millimeters. Okay, good job. We're using the metric system. So your science teachers can be happy. Math and science are good partners. All right, so here's your assignment. It's also in the bottom of your sheet. It looks like a lot, but some of the first ones are, is it a reduction or a dilation? Or a reduction or a enlargement?